Hi student. In last lecture we discussed about conformational isomerism in organic compounds. This isomerism also exists in inorganic compounds. For inorganic compounds we can also draw conformers that can form due to the rotation about a single bond. For example, hydrogen peroxide can exist in two different conformeric forms. Hydrazine can also exist in two different conformeric forms. This compound can also exist in two different conformeric forms. For example, for hydrogen peroxide, we can draw either this type of conformer or this type of conformer. These two are possible because of free rotation about this OO single bond. Similarly, for hydrazine, here I can also show lone pair of electron of this oxygen atom. Then it becomes significant. Here there is a more repulsion between these lone pair of electrons of oxygen. For hydrazine, nitrogen is in tetrahedral arrangement. This is the tetrahedral arrangement of nitrogen. Here it is nitrogen, not hydrogen. And in second structure, due to the rotation about this N single bond, a new structure may have formed in which repulsion between this N bond is less. All these angles are tetrahedral angle around this nitrogen atom. Now, for 1,4-dihydroxybenzene, two different conformeric structures are of this type. So it is because of rotation of this CO bond. If the CO bond get rotated in this direction, we will get this conformers. So there is a lot of application of conformational isomerism or conformers. For example, if we have to compare dipole moment of dipole moment of eclipsed 1,2 dichloroethane and eclipsed 1,2 dichloroethane and compare dipole moment of various conformers of 1,2 dichloroethane. So 1,2 dichloroethane is CH2Cl, and this 1,2 dichloroethane exists in four conformeric forms. This is the first form. This is second form. This is third form. And this is fourth form. So dipole moment in this compound is mainly due to carbon-chlorine bond. And in carbon-chlorine bond, carbon is partially positively charged and chlorine is partially negatively charged. And because of this carbon-chlorine bond, dipole moment is towards chlorine atom. Direction is towards chlorine atom. So in first compound, the dipole moment of this carbon-chlorine bond is towards chlorine and this is also towards chlorine. So its dipole moment is not equal to 0. While in this case, dipole moment of this carbon-chlorine bond is towards chlorine and it is also towards chlorine. So dipole moment of second form is also not equal to 0. Now in third case, again dipole moment due to carbon-chlorine bond is again towards chlorine and its dipole moment is also not equal to 0. But in fourth form, dipole moment of carbon-chlorine bond is towards chlorine atom and these two bonds are at 180 degree dihedral angle. So its dipole moment is equal to 0. And now we can arrange them in the order of their dipole moments. The dipole moment of antiform is 0 and that of fully eclipsed, partially eclipsed and Gaussian form is not equal to 0. When we compare their magnitude, it is clear that dipole moment of fully eclipsed form is more than that of Gaussian form, and that is more than that of partially eclipsed, because dipole moment is a vector quantity. The resultant dipole moment is vector sum of all bond moments. Bond moments is dipole moment due to a particular bond. So dipole moment due to this bond is called as bond moment, and dipole moment due to this bond is called as another bond moment. And resultant dipole moment of this molecule is vector sum of bond moment, vector sum of dipole moment of these two bonds. First, we need angle between these two dipoles. And angle between these two dipoles is 0 degree. So resultant dipole moment will not be equal to 0. To find out the vector sum of these two vectors, we need the angle between them, that is cos theta, and theta is equals to here 0. While here the value of angle is 60 degree, and here the value of angle is 120 degree, and in last case it is 180 degree. So resultant dipole moment comes out to be 0, because these two vectors are equal in magnitude and opposite in direction. These two are equal in magnitude and opposite in direction. So it will get cancelled out. So as the angle between two dipoles increases, resultant dipole moment of the molecule decreases. So the order of dipole moment is dipole moment of first compound is more than the dipole moment of second compound, and that is more than the dipole moment of third compound, and that is more than the dipole moment of fourth compound. So remember that for symmetrical molecule, dipole moment of anti-staggered form will be 0. For this 1,2-dihydroxybenzene, dipole moment of this form is 0 and that of this form is non-zero. Because dipole of this carbon-hydrogen bond will not cancel out, while here it will be cancelled out. Because all other are fixed on their positions. So its dipole moment is not equal to 0, while its dipole moment is equal to 0. If this OH bond and this OH bond are in the same plane. If again these are in this alternate at an angle of 90 degree, then it will not be equal to 0. Means these bonds are in the same plane. This OH bond and this OH bond both are in the same plane, in this plane, like in this way. And here these two are also in the same plane, but in opposite direction, in this way, like in this way. These are in the same plane, but in opposite direction. Like in this way. These two are in this way, while these two are in this way. So this is the application of conformational isomerism. Now cyclic compounds also exist in various conformeric forms because of non-planar ring structure. So next we will discuss conformers of cyclohexane. Cyclohexane is non-planar molecule because all carbon atom of cyclohexane are sp3 hybridized, and all these sp3 hybridized carbon atom cannot exist in same plane. In this angle cannot be 120-degree angle. So because of the non-planar puckered structure, various conformations of cyclohexane are possible. So cyclohexane mainly exists in two conformeric forms. The first form is called as boat form, and second form is called as chair form. So this is chair form of cyclohexane, and this is boat form of cyclohexane. Now, in chair form and boat form, all the carbon-carbon-carbon bond angle are very close to 109.5 degree. And actually these are 111 degree bond angle. So now on every carbon atom, there are two different type of bonds called as axial bonds. Are in upward direction. All are the axial bonds. And the second type of bond is called as equatorial bond. Here there is one more axial downward, 6 axial and 6 equatorial. Similarly, this is axial equatorial, axial equatorial, 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 and equatorial. So cyclohexane exists in two conformeric structures. All are the hydrogen atoms. In chair form, This is footrest and this is headrest of this chair. So this chair can be converted to other isomers. So chair form can be of this type or it can be of this type. These two chair forms are in dynamic equilibrium. So there is flipping between these two different chair forms. If footrest carbon is pulled upward, then it becomes boat form. And in between chair form and boat form, some other forms are also possible, like half chair. Half chair can be drawn in this form. This is half chair. And we can also draw twisted boat form. But these are comparatively less stable form of cyclohexane. These are less stable form. These two are more dominating form of cyclohexane, chair form and boat form. So chair form is more stable and boat form is less stable, because in boat form there is more repulsion between these flagpole hydrogen atoms. These two positions in boat form, like 1, 2, 3, 4, 1, 4 positions are flagpole positions. And there is a strong repulsion between hydrogen of these flagpole positions. And there is a less repulsion between these positions. First of all, this C4 hydrogen of C4 position and this hydrogen of C4 position, C1 position, are in downward direction, upward and downward direction. And there is a less repulsion between this hydrogen and these two hydrogen atoms. This is the position of these hydrogen atoms bonds. This is this bond, and these two are these bonds. So there is a very wide gap between these positions. And remember that all bonds represented by red lines are axial bonds, and all which are represented by blue lines are equatorial bond. So this is the axial bond and this is equatorial bond. So the axial bonds of adjacent carbon atom are in opposite direction. If axial of this carbon atom is down, then axial of its neighboring carbon atom will be up, then axial of its neighboring carbon atom will be down. So down, up, down, up, down, up. Similarly, equatorial of this carbon atom is downward, while equatorial of this carbon is upward. It's moving downward, projecting downward, and it is projecting upward. So remember that space at equatorial position is more than at the space at axial position. So bigger size substituent always occupy equatorial position or positions. If there are more than one substituent, then it always occupy the equatorial position. Suppose if we have 1,2-dimethyl cyclohexane. Now this 1,2-dimethyl cyclohexane can exist in three structures. Suppose this is 1 and this is 2. This is the first carbon atom and this is second carbon atom. First carbon atom and second carbon atom. First carbon atom and second carbon atom. 1, 2, 3, 4, 5, 6. So now I want to place two methyl substituents on these positions. So first possibility that both of them are on axial positions. So axial 1,2-dimethyl cyclohexane. In second possibility, both of them can be on equatorial positions. So equatorial 1,2-dimethyl cyclohexane. And in third possibility, it can be axial equatorial 1,2-dimethyl cyclohexane. So this is axial, this is equatorial, and this is axial equatorial. So order of stability of these three forms of cyclohexane is 2 is more stable order of stability. 2 is more stable than third form because here both of the substituents are on equatorial positions. Here one of them is on equatorial positions, while this is the least stable because both the bigger size substituents are on axial positions. So this is because of existence of cyclohexane in more stable chair form, and in this more stable chair form there are two different type of positions on every carbon atom, axial positions and equatorial positions. On these positions, hydrogen atoms are placed. So space at equatorial position is more than the space at axial position because equatorial position is extended outward, away from carbon atom, while axial positions is extended less extended outward. Equatorial positions is extended more outward. So space at equatorial position is more than the space at axial position. So bigger size substituent always occupy equatorial position to have a more stable arrangement, more stable structure. So it's all about conformational isomerism and conformers of cyclohexane. Now finally in this conformational isomerism I want to discuss the curves that can be drawn between energy content of different conformers and angle of rotation. So for ethane, you know that two conformers are possible. One is eclipsed and second is staggered. So this is the eclipsed ethene and this is staggered ethene. Energy of eclipsed ethene is more than that the energy of staggered ethene. So if we draw a curve between angle of rotation on one of the axes and free energy of these conformers. So this is 0° dihedral angle, this is 60° dihedral angle, 120 dihedral angle, 180 and so on. So at 0° dihedral angle, the form that will exist is of higher energy, that is eclipse form. And at 60° dihedral angle, the form that exists is of lower energy and staggered form. And again there will be staggered form, eclipse form, higher energy form and lower energy form. So curve move like in this form. So again it will move to the second position. So if I take one more angle, so it will be 240°. So all these forms are of same energy. They have same energy. So this is first form, this is second form, this is again first form, this is second form, and this is again first form. And the barrier of energy between first form and second form is very small. For ethane it is 2.5 kilocalories per mole. 2.5 kilocalories per mole. Now, if we draw the similar curve for butane of its conformer with respect to C2C3. First form, second form, and third form, fourth form. Now we know that order of energy of these forms is in this form: first greater than third, because the eclipse form is less stable than staggered form. So energy content of eclipse form is more than that of staggered form. Then the second form, and then the fourth form. So now if we draw a curve between angle of rotation and free energy change, free energy content, then you can say this is the 0° dihedral angle. This is 60-degree dihedral angle. So this is 60-degree. So this is 60-degree dihedral angle and 120-degree dihedral angle, 180-degree dihedral angle. And again you will notice that it will be 240-degree dihedral angle and 240-degree, then again we will rotate by 60-degree, then we will get the another angle. So just I want to draw till 180-degree dihedral angle because we have taken only 4 conformeric structures. So this is the first form, and then this is the form with 60-degree dihedral angle, and this is the form with the 120-degree dihedral angle. Degree dihedral angle. (120-degree dihedral angle) and 180-degree dihedral angle. So curve moves in this way. So this is the first form, this is second form, and this is third form, this is fourth form. When you rotate fourth form by 60-degree dihedral angle in clockwise direction, you will get a third type of form, and that on further rotation will be converted to second type of form, and that again you will get the first form. So this type of angle of rotation. So we can get these various conformers and their position in energy and angle of rotation curve. So no need to remember the exact value for the energy barrier between any two conformers. Just remember them in qualitative form, not in quantitative form. Qualitative form means to say the anti-stagger will be more stable than quasi-stagger, that will be more stable than partially eclipsed, and that will be more stable than fully eclipsed. So it's all about conformational isomerism. So this section is complete. Conformational isomerism is complete. In next class we will discuss geometrical isomerism. Till then, again you must revise it properly before coming to the next lecture. Now I end my lecture here. Thank you very much.